Hi, I'm Ori. Today I'm gonna talk about how we are solving the halting problem for Starknet. That's a bit extreme, but actually, how do we prevent attacks on Starknet from users that try to run infinite loops? The main scenario we're gonna discuss is this. User sends this code to Starknet. This code is a recursion that would never stop because it has no stopping condition. We need to stop this from happening. Otherwise, we would need to detect this happening and won't be able to prove the fact that it happened and charge the user. First solution that we can do is simply adding a gas counter in code. What we're going to do with the gas counter? Oh, I just deduct from it, and whenever I ran out of gas, I panic with out of gas, and all is hunky-dory. We prove the user have ran out of gas, improve the entire run execution, it's all good. But this is user code. How can we actually make sure the user actually added gas counting information here? So a reminder, in Shachar's lecture that I hope you've been to yesterday, otherwise I would give a quick reminder anyway. We have a Sierra, which is a safe intermediate representation that this is a sort of code we are going to accept on Starknet. It is a very structured IR, meaning we can add simple constraints on it to make sure that the user of this code provided us with any information we actually require. So, using Sierra, we can just inject a gas change and check per command. If we've got this code, you can ignore the actual content of the code, but believe me, it's some sort of Fibonacci implementation that sort of look like Sierra. We can add a get gas statement and failure in every line. I try to get gas. If I succeed, I continue. If I fail, I panic. Since the user did not actually send the code, everyone's happy. But we can actually, if we ran out of gas in this line, we can prove I got to this line and we ran out of gas. So we were happy. Issue. Some functionalities are much cheaper or pricier than others. For example, obviously getting the constant one is much cheaper than actually calling the Fibonacci code itself recursively. Okay, let's try another solution. We can inject a gas change, but having varying costs. Same code. This time I ask for differing amount of gas per command. Okay, so we solved the varying prices issues, but still, this adds an additional gas check for every command, which makes at least all the cheap commands at least twice as pricey. And also, it means that every command may fail, which, first of all, still makes everything pricier. Second of all, if some of you remember Shachar's lecture, there are some specific instances that we have to call code, which means we can exit the code at every point in time. If you can exit the code at every point in time, it means we need to do some sort of special error handling to make sure the code is still provable, which is pretty difficult. Solution, the gas wallet. What is a gas wallet? A gas wallet is a compile time solution for us to know that the submitted code, the submitted user code, is specified to some constraint about gas usage. With the specific example, what we're actually doing is in compile time, we are bookkeeping some sort of gas wallet, while when we add each and every command statement we are trying to add it to the run, we can deduct from its price from the local wallet, and we validate that you never actually ran out of gas in this wallet. This is the simple constraint we added to Sierra here. And we added a new special command for get gas, which is the only command that can actually fail. when I try to call getGas, I can fail and exit the program, which means the only place I need to actually handle errors in these sort of focal points. So our Sierra code now would have a simple additional getGas in the beginning. I ask for 30 gas units, and I know I can at least run the code until the next time I would get to getGas. We would run through a very simple example now. Let's assume I have 5 available steps in my wallet. I'm calling the getGas. If I failed, I would exit. Assuming I succeeded, after this line, I've got 35 available steps of gas. I'll try running. And this branch, I take 1 step. The add costs another one. The cost and the rest of the, until the function call, costs an additional 6. And on the other example, I got to the other branch. I only took the price of the first action. But in the merge, I would use the worst possible case here. I still made sure that I haven't run out of gas in any of the branches. And I'm still happy, and I know that I can verify in the compilation stage here that I never actually would be able of running out of gas without marking it in the actual in my actual gas counter that is provided for the context of the running program. As I mentioned earlier, we've got the issue with Sierra linear types. In Sierra variables, we must destroy or return all the variables. Some of this may be quite heavy. For example, disk squash. Disk squash is after I do any sort of dictionary accesses, I gotta do a disk squash in order to be able to prove the fact that these sort of accesses were actually valid. Otherwise, it means my code is not sound. Meaning, in Sierra, we make sure that every time I construct a dictionary, I need to destroy it using disk squash. But if you look at this example, there's no dictionary here, but if there would have been, the getGas command, I said it panics, I still need to make sure a squash is called. Why is that an issue? So that could be an issue because I said I panic out, and I still need to make sure that I call this command. And disk squash specifically is a pretty expensive command. Its actually costs, its cost corresponds exactly to the amount of accesses that actually happened. Meaning, if I did a lot of accesses there and I ran out of gas, now I need to call a very heavy command while I ran out of gas, which means someone can make me use a lot more gas than I actually plan to. The trick here is pre-charging the cost. As I said, the squash command corresponds to the amount of access to the dictionary. So despite the fact that access to the dictionary is not that pricey by itself, I will pre-charge the price of destroying this access in the squash stage during the access stage. So instead of the actual cost of, let's assume, 12 steps for reads and writes, and the actual 100 plus 70 for the number of access, instead I would actually charge at the time of the accesses plus the 70 for the access itself, which means that even though I ran out of gas, I already pre-charged all the problematic parts of the squash command, so I'd be able to call it. Another issue is in the case of deconstructor loops. For example, if I have an array of such dictionaries, I still need to call the squash of all the dictionaries, right? Because I said, if I don't squash all my dictionaries, my code is unprovable. So somehow I must be able to call them. What would I do? Instead of having an array of the heavy object, I have an array of the heavy object plus a gas coupon. What's a gas coupon? I can call the gas coupon, create a gas coupon. It would deduct from my local wallet, but it would create an object that once I decide to release, I give back into my local wallet. So even though I called getGas somewhere entirely different, I already pre-charged for this destruction command. So when I have the array of heavy plus coupon tuples, I can just iterate over it, redeem the coupon, and heavy drop. And despite this seems that it should cost amount of gas that corresponds to the size of ARR, it actually costs 0 because the coupon itself gave me an existing gas to be able to redeem it and do this all at this, even though I already ran out of gas. Just a small example, this is actual Sierra code in an annotated level, but you can see that one of the first commands is actually as if there's an if on get gas and handling of the error case in case of the actual failure in our generated code. Another things we can solve here is prices for dynamic cost sort of objects. For example, hashes may have dynamic costing, and other built-ins may have dynamic costing, and we don't want to ahead of time say, I don't know, Peterson cost 100 units of correspond to 100 steps. I want the OS to be able to decide what is the cost of Peterson hash, for example. So instead of only having the steps token, the step token type inside my local wallet, I can do the exact same process that I described earlier for other kind of steps, and still bookkeep for each and every one of these, and make sure it never goes negative, and make sure I can get the gas for it. Of course, getting gas for something that I decide has a non-constant cost would be a bit pricier, since I need to calculate the amount of actual gas I want to take from some price table given to me by the OS. So yeah, that was the main part of the presentation. If you want some questions about Sierra generally, about specifically what we discussed here about our ability of how to solve gas, ask away. Yes.
In the slides, I saw you are charging less fee for
Squash?
So what happens if it requires more gas to
Here?
this slide?
Yeah. What about it?
Is it actually cost less than the charges, right?
The total cost in both cases is exactly the same, although I pre-charge everything in this case. That's the idea, that I won't be able to create enough accesses that create the squash. If I would have ran out of gas, I would have ran out of gas earlier, and still would have needed to call the squash, so I can still prove the exact process of the, I would still call squash, so all my code would be provable. Anything else? Yes? Okay, so the question here, if I can basically bound an area of code to have a specific gas bound, right? Or on the transaction level. So if I won't have a get gas command and have no if I have any recursive code, by definition, I don't know the amount of gas I'm going to take. So I would have to have some sort of get gas command, and I would need to check it and deduce from some sort of actual gas counter. But if I have no recursion at all, I can actually know the exact cost of calling the function, and it would be entirely fine as long as the entry point itself would still need to decide, I need to make sure this user had enough gas in his wallet to call this, and it would be deducted from his account. Yes? No. No, this is all in Sierra level. The actual submitted Sierra code is going to have like gas instances, but this is mostly going to be hidden unless you really don't want it to be hidden. Yeah. Yes?
Can you talk about what brings about cost in Sierra and why? For instance, read and write being the same cost seems somewhat surprising.
That read and write for the dictionary of the same cost?
Yeah, talk about what is costly in Sierra.
So dictionary specifically it's a completely different subject, but the dictionary itself is a set of accesses that later I validate that it makes sense. The squash action is validating that the previous accesses made sense. So an access of read and write is basically the same thing. I just need to make sure the series of accesses makes sense, and that's a squash command. Yes.
Maybe I didn't understand very well, but on the pictures you showed, there was no like gas check for the return statement.
For the return statement?
Yeah, if I remember well, there was no gas check.
Which one? The actual code or
Yeah, like typical.
or the? I mean, there's. I need to know
I think it was the first one we were showing
here.
here. Typical. You're taking almost everything except the return.
Yeah, it's fake code anyway. I mean, it doesn't actually.
The return statement has a gas cost.
The return statement doesn't have a gas cost just because the call statement has a gas cost of 2. So just amortized make the same amount of sense. But yeah. Yes.
What's the main difference between Chiron and Solidity that makes Chiron need this solution?
So first of all, our necessity for linear types makes us have to handle every exit point to make sure all the variables are destroyed or are no longer available, not necessarily destroyed. So we got to handle each and every exit point. Having less exit points makes it much easier. In EVM, as far as I know, every command can fail by running out of gas, varying amount of gas, but still running out of gas. Anything else? Yes.
Squash command, you basically roll the variable to the dynamic cost into the reads and writes,
Yeah.
but the squash itself still has a constant cost in it. Why is
It
that?
has.
Why isn't that just part of the construction cost?
You can borrow it into construction costs as well, but in every flow, in every running flow, you always have the new and the destruction in the same flow. So I don't really care if it's amortized there or not.
In my head, if you charge it later, you get to use more gas.
But it's not really because you still deduce it to begin with. So that.
There's no loops in the way, sure.
Yeah, but if it's still not actually going to matter there. But it makes it easier to. We have some sort of auto step counters, making sure our code generation makes sense, and it's much easier that way if we actually charge whenever it's actually charged as much as we can. Yes.
Makes the CI code easier. What if you don't want to do a smart contract but want to use Chiron? Is there a way to export it to Sierra without the gas management?
Yeah. I mean, at least currently we can compile Sierra without a gas constraint. Yes.
You calculate the gas based on the worst possible scenario, right?
That was a bit of a lie. We are actually by hand realign these, and we can actually refund gas counters for alignment. We're not actually doing that currently, but we can do that.
The question is, if I were to have 2 functions, could be in the worst case scenario be taking a lot of gas, but in practice, the first one takes a little gas and the last layer up takes a lot of gas. And in theory, I could run them both, but
So the optimized scenario would be handling the gas counter, that the compiler would handle the gas counter and refund the gas for that case. And yeah, still got a minute if anyone wants a couple. Yeah.
when there will be for loops, each entry into the for loop will cause down gas call?
Yes, but if it's too small of a loop, you probably do some loop unrolling, so you'd only get gas once any, I don't know, 4 iterations or whatever. Yes.
I mean, if the contents are static inside the loop, then you know the cost per loop.
If you unroll the entire loop, that still makes the same amount of sense.
Also, if you know the cost, the start of the loop in advance. Right?
If you know the cost of the loop in advance, you can also do the coupon method anyway. Anything else? Yes.
Why do I need
The since if I need to destroy an arbitrary amount of dictionaries, I need to iterate over them. For the iteration itself, even just the iteration code would have to cost some gas. So I need to pay for it somehow. Okay, thank you very much.